Okay, welcome back. So we're going to be on the third question now, and it asks us to convert the IUPAC name into the drawing. So I have here B and C. You can do A on your own. We're going to look at these two examples here. So from the name, it gives us a lot of information already. We can see the kind of substituent. We can see, or actually, first of all, we can see the parent name, or like what kind of alkyl chain we're dealing with, where you can see the kind of substituents that are there, as well as where those substituents are located. There's a sec butyl at carbon 4, an isopropyl at carbon 3, a methyl at carbon 2, and we know that this carbon chain has 9. The longest carbon chain is 9 because it's 9. So first of all, let's just try drawing the longest chain, right? And that's 9. 2, 3, 4, 5, 6, 7, 8, 9. Right? And then I like to just number it going from left to right because it's pretty easy for me. Then we just draw in the substituents. 1, 2 is a methyl, 3 is an isopropyl, and 4 is a sec butyl. There we go. And if you don't really know the difference between an iso, sec, or tert butyl, let's go over that really quickly. Okay, so here we have a sec butyl. Here we have a sec butyl. We can see that over here we can label this whole thing as the R group and this as the sec butyl. And we can kind of imagine that if we were to number it like its own chain, we can see that 1, 2, 3, 4. Then the R group, this whole thing here, is attached to carbon 2 of this mini chain. We also hear of isobutyls. If we were to I guess you can kind of think of it as like a Y, because you got that like Y shape. Sometimes I like to think of it as, we have 1, 2, 3, 4 carbons, and then this R group is attached to this first carbon right there. Iso in the name means isolated. Think of that how you will. So this is an isobutyl. And then, let's do that. And then a tert butyl. There's not really much I will say about this one. Kind of just looks like a chicken foot. That's usually how I like to think about it. Just looks like a chicken foot. Now, you may have noticed that in the naming, we don't really alphabetize the isopropyl. I'm sorry, no. We don't really alphabetize the S in sec and the T in tert butyl. We only alphabetize the iso. That is one thing you should probably note. Okay, now back to the other one. Again, looking from the name, we see a lot of information here. We see the longest chain is an octane, meaning 8. We also see that an ethyl is at carbon 6, a methyl is at carbon 2, and something called a 1-methyl ethyl substituent at carbon 5. So let's just first get our bearings on the longest chain. Okay. Now we have a methyl at 2, and ethyl at 1, 2, 3, 4, 5, 6. Something called this 1 methyl ethyl at carbon 5. That's just right here. So really, that substituent, you can kind of see it in the name, right? It's an ethyl, so like, let's have this whole thing as an R, right? We're just gonna box this whole thing as an R. Remember our radical fragmentation. And then an ethyl, 1, 2, and a methyl at carbon 1. So really, it is just an isopropyl, but kind of confusing name. Good job if you got that part on the first try without this video. I'm very proud of you. Proud of all of you, honestly. Good job. Anyway, and yeah, there you have it. 6 ethyl, 2 methyl, 5, 1 methyl ethyl octane. Okay. Another one you can try on your own. I will not be going through that. Okay. Number 4 asks us to identify the functional groups in the compounds below. Right off the bat, I will tell you that functional groups is something that you have to familiarize yourself, as there's so many. There's not really much of a logic to be said about functional groups. Flashcards are the best way to go if you want to familiarize yourself. So we can take something like a diazepam, the one in the bottom. That's a This is a diazepam, right? Functional groups that I can immediately see is this amide or amide, right? If you think about it, amides are kind of like esters. This is an ester. And this is an ester. This is an amide. The difference is that we're replacing this oxygen with a nitrogen. Amide, right? And if you want to even simplify, like, I always think that esters and amides are always bigger versions of, this one's a very simple, I don't want to use, always bigger versions of their little ones. And so esters kind of look like an ether, right? Kind of looks like an ether. And an amide kind of looks like an amine. NH2. Let's call that carbon, right? This is an ester. This is an amine. Now, in classes, we've heard that there are different types of amines. There's primary, secondary, tertiary. Let's go over that real quick. And it really just differs based on how many R groups are attached to that nitrogen in the amine. So we have So, looking at it from left to right, we can see that this is a primary because there's one R group attached to this nitrogen. There is a secondary because there's 2 R groups attached to this nitrogen, and a tertiary because there's 3 R groups attached to this nitrogen. Okay, what else can I see aside from the amide? That's our what? 8, 1, 2, secondary and mid. And then we also see this thing right here, an aryl group. Aryl, but more specifically, it is a phenyl. Phenyl. Okay. This one, this substituent is like an aromatic ring. Aromatic. But specifically because there's a chlorine attached to it, it is a chlorinated. Chlorinated. A lot of things, a lot of functional groups you can see here, right? Another thing is the difference between a phenyl group and a benzyl group. Let's erase all this junk. Yep. So the difference between a phenyl group and a benzyl group. They both contain a benzene or an aromatic ring. However, the benzyl has one carbon and then the R group, while this phenyl, let me actually write that. While this phenyl contains no carbon and then just this R group. This is a phenyl. So both aromatic, benzyl contains one carbon, then R group. Phenyl is just directly bonded to the R group. So if you look at diazepam, you can see that there is a phenyl. And you can also see that in warfarin on the worksheet as well, and atropine. Yep. So again, functional groups is all about familiarizing yourself with all of them. There's a whole ton of them for you to look at. Flashcards are the best way to go. Okay. Number 5, Lewis structures. And formal charge. Formal charge, there we go. So slanted. Let's look at the first one together. Right. So Lewis structures are what you've seen in general chemistry. Are structures, line bond drawings, that include the lines and dots. The dots they represent lone pairs, lone pair electrons. So since this oxygen only has one bond connected to this carbon, it needs 3 other lone pairs to have its octet. 1, 2, no, that's just 1, 2, 3. And then this nitrogen has 1, 2, 3, 4 bonds. Can't really have a lone pair there. So nitrogen usually likes one lone pair. Here it doesn't. So we need to look at its formal charge, right? So we can actually mathematically derive this formal charge. Fc equals the number of valence electrons minus the number of non-bonding minus the number of bonding electrons over 2. Okay. Or you can kind of just recognize that if this nitrogen doesn't have like one lone pair, then it has like a plus charge, etc. I guess you can kind of shortcut it by looking at the periodic table and say like, oh, how many valence electrons does this atom has? And then you can count, like oxygen likes to have 6 valence electrons. Right, 6 valence electrons. 1, 2, 3, 4, 5, 6, 7 valence electrons, so it has a minus charge, right? Nitrogen likes to have 5 valence electrons. It has 1, 2, 3, 4. Does not have a fifth valence electron, so it has a plus charge, right? Calculating the net charge is just counting up all the charges together in this whole molecule, and we should have a net charge of 0. Let's look at Let's look at the third one on the bottom. You can try the second one on your own yet again. Okay, so we need to include the lone pairs as part of our Lewis structure. So this one also has a lone pair. 2, 4, 6. This one has a lone pair. These have lone pairs. There we go. This one has 6 lone pairs. What the hell? 3 lone pairs because the oxygen is only bonded to nitrogen once, right? Except for this one. So let's start off with this one, this nitrogen here, right here. This nitrogen likes to have 5 valence electrons. We can count 1, 2, 3, 4, 5. 3 of those valence electrons are being used to covalently bond to other atoms. So regardless, it has 1, 2, 3, 4, 5 valence electrons. So it has a neutral charge. This oxygen likes to have, let's say, 6 valence electrons. Right here, it has 1, 2, 3, 4, 5 valence electrons. Let's draw in the bond right here with the hydrogen. 1, 2, 3, 4, 5 valence electrons. So this has a plus charge. Nitrogen likes to have 5 valence electrons. We can see that 1, 2, 3, 4. Oh no, it has a plus charge. This oxygen likes to have 6 valence electrons. 1, 2, 3, 4, 5, 6. So it has no net charge. It has all its valence electrons with it. This one as well also likes to have 6 valence electrons, but it has 1, 2, 3, 4, 5, 6, 7. Well, that's one more, so it gets a negative charge, right? And then we can count up the charges all together to get its net charge. A plus, plus, and a minus. That brings us to a net charge of +1, right? If we want to use this little formula right here, let's take, for example, this oxygen. This oxygen has valence electrons of, let's say, 6, right? It has 2 non-bonding electrons, this one pair, minus the bonding electrons. 1, 2, 3. Over 2. And that gives us, wait, that's 4. I need my calculator. Let me see. 1, 2, 3. I guess actually, because it's bonding electrons. So it's 2, 4, 6. Yeah, I believe it would be 6. So this would be 4, 3. Minus 2 minus 6. 6 minus 2 is 4 minus 3 is equal to +1. There you go. The bonding electrons, you would count 2, 4, 6. 2 for each bond it has, right? If you want to do it for this nitrogen, nitrogen likes to have 5 valence electrons minus the non-bonding, which is 0, because it doesn't have any lone pairs, and then minus the bonding electrons, so 2, 4, 6, 8 over 2. This becomes 4 minus 5, and so this nitrogen has a +1 charge. That's how you can use that formula. Okay. The last one you can do on your own. Very fun, exciting. Okay. So the last page talks about resonance. My favorite, also the topic that a lot of OChem students have trouble with. Let's try doing one. I made this worksheet in advance when you guys were going to talk about resonance after. So this is kind of like a little bit of an exercise, I guess, for future you. So let's do 6 resonance. So as a refresher, what exactly is resonance? I like to think of resonance as kind of like constitutional isomers, but we're not moving around atoms. Instead, we're looking at the movement of electrons between atoms, right? So if I have this simple ketone here, we know that this oxygen, let me draw that bigger. Here we go. If I drew this huge simple ketone right there, we know that this oxygen can hold more electrons, right? We've seen that oxygen can hold 3 lone pairs. So how do we do that? We simply move these electrons upwards with this double-headed arrow. A double-headed arrow means we're moving 2 electrons, while a single-headed arrow, which I don't believe you'll be doing anytime soon, moves only 1 electron. So when we do this movement of electrons, this is a delocalization. We're spreading out electrons between atoms so we can see different points of reactivity in this molecule. Right? Here we have a plus charge. You can actually see a pattern, a carbon bonded to something electronegative, something that really wants electrons. They're greedy, they want more, right? So we have forgot what this is called. Actually, I forgot what that's called, but I know that this points upwards due to electronegativity. Becomes partially positive, partially negative. When we do resonance, we can see a total negative charge and total positive charge, but they flip between. Actually, they don't flip between. Scratch that. They don't flip between. It's actually a combination of both. And you would represent that as a dotted line with the positive and negative partial charges. So one thing we can note is something bonded to electronegative atoms. We can also see that the atoms can hold more electrons. Oh, that's so ugly. I'm sorry. Bonded. Electronegative atoms can hold more lone pairs. And I've also used a double-headed arrow and some brackets. So we do not not confuse ourselves that no, this is not an equilibrium. However, yes, there is a major contributor and a minor contributor that we will talk about next time. So let's do the first example on our own. I mean, not our own, together. We're going to do the first one. Okay, so we have our first molecule. When you're doing resonance, always include the lone pairs. This doesn't need lone pairs, so it has a plus charge because of the formal charge. 1, 2, 3, 4 valence electrons. It is lacking 1 valence electron, so it has that plus charge. Okay, and we are looking at something, we are looking at the movement of electrons. We're looking at the movement of electrons between something electron rich to electron poor. I don't think you can see that, but it says electron rich, right? And so where are the electron rich areas? We know that pi bonds contain electrons, right? Do not break sigma bonds. You can break pi bonds, but not sigma bonds. Pi bonds are like extra sources of electrons. They're like more money. This nitrogen does not have any money. He needs money. This pi bond is like, oh my gosh, I have a lot of money. This carbon shares a pi bond with nitrogen. It's like a shared account. When nitrogen says, hey, I need more money with this plus charge, this carbon is like, oh my gosh, sure, I can give you that money, right? When we pour in all those electrons into nitrogen, I'm going to call this R, right? This nitrogen now has lone pairs. Oh my gosh, it has money. It's good. It's happy. We all love money, right? Oh my gosh. So, but now this carbon doesn't have anything. No electrons. Or well, it has electrons, but it's lacking because it gave away. So where else can I find extra electrons? More money, right? This pi bond can whoop-de-doo give its electrons over to this carbon while also not breaking its octet. This carbon is not breaking its octet because if we do this, just making sure you can see. Bam. Because we can see that this carbon right here has oh my gosh, wait, 1, 2, 3, 4. Okay, I'm not joking. It has 4 bonds, right? We're not violating the octet rule. Instead, we are just moving electrons to places that are electron rich to electron poor areas. So, since this pi bond moved there, this carbon now becomes electron poor. Where else can we move it? Lone pairs that are adjacent or next to areas that are electron poor are great places for resonance, right? We want to share this positive charge. Sharing is caring. Always sharing is caring. Let me sit. Let me find this one. Okay. H, bam, bam, right? But now we also need to know, we have to put in our charge. This nitrogen shared its electrons. It likes 5 valence electrons, right? There's 1, 2, 3, 4. It needs a plus charge. It needs a plus charge. Because it doesn't have that valence electrons. This also needs a plus charge. Lone pairs, right? So, something you can see is that we are moving electron-rich stuff into electron-poor stuff. More money into less money. Sharing is caring. Be philanthropic. Generous, right? Always good. Electron-rich, electron-poor, electron-rich, electron-poor, electron. I guess it can cycle back, right? Another thing you can note is that our original structure started off with a plus charge. The net charge was positive 1 to be exact, right? Positive 1 net charge. When we look at the other structures, they are also positive 1. We do not want to create a different structure with a different net charge. That is not a valid structure. Is there anything else that I'm missing? Yeah, that's resonance for you. So let's do a second one, a second example. Let's do the second one. There we go. Okay. Very good. Excuse me. Okay, so we have our original structure. We need to know whether there are atoms that can take in more electrons. Are they greedy? Are they electronegative? Where on this can we see that? Nitrogen, sure, it's kind of electronegative, but something even more electronegative than nitrogen is that oxygen. Greedy, right? Wants more electrons, so we can move the pi bond here into the oxygen, because oxygen can hold 3 lone pairs, right? To achieve a negative charge. So draw the lone pairs. There we go. H2N. There we go. Okay. And now really, it's like filling in more buckets, more empty buckets. Something full of electrons into something poor of electrons. This is a plus charge. So we're moving something electron rich into something electron poor. And you can see that these 2 carbons shared a bond, right? This carbon was like, okay, yeah, sure, I'm fine with giving away, I'm sharing with another person, another carbon, right? So now this carbon has a plus charge because it only has 2, 4, 6, that 1 hydrogen. Because originally it had only 1 hydrogen here. Let me draw that in. Okay. So it only has 2, 4, 6. 1 hydrogen. Now we do the same with the other ones. Electron rich, electron poor. And then we have, this one has its octet, this one does not, so it has a plus charge here. And then we can do our last structure here. This lone pair on a nitrogen can donate to fulfill that positive charge. I am so hungry, oh my god. H2 and a positive charge, right? And in brackets. Okay, so in each of the structures, we can see that the formal charge hasn't changed, right? The net charge, at least. This one has 0 net charge. This one has a positive and negative, canceling each other out, so that's 0. This one has a positive and negative, that's also 0. Positive, negative, 0. Positive, negative, also 0. Valid Lewis structures, valid formal charges, valid resonance. We're not breaking any sigma bonds. We are not forming Texas carbons. Never do that. We are forming valid Lewis structures that have all of their, all of the atoms full octets. And resonance helps solve that burden of having less than 3 bonds, right? So yeah. So that's all for today. Thank you guys for watching.